Classical mechanics is great. If you know the state of a system, say the position and velocity of a particle, then you can use an equation, Newton's second law, to calculate what that particle will do in the future. In quantum mechanics, if you know the quantum state of a particle, that is, its wave function, you can use the Schrödinger equation to calculate what that particle will do in the future. Usually, it spreads out over time as it is doing here. Note, to make this animation, we really solved the Schrödinger equation. So there's a beautiful symmetry here. If you know the initial state, you can use an equation to evolve that state smoothly and continuously into the future. The problem is, in quantum mechanics, we never actually observe the wave function like this. Instead, when we measure it, we find the particle at a single point in space. So how are we to reconcile the spread-out wave function evolving smoothly under the Schrödinger equation with this point-like particle detection? So the way quantum mechanics came to be understood, and the way I learned it, is that there are two sets of rules. When you're not looking, the wave function simply evolves according to the Schrödinger equation. But when you are looking, when you make a measurement, the wave function collapses suddenly and irreversibly. And the probability of measuring any particular outcome is given by the amplitude of the wave function associated with that outcome squared. Now, Schrödinger himself hated this formulation, which is actually why he invented the famous Schrödinger's cat thought experiment. Put a cat in a box with a radioactive atom. Add a radiation detector that triggers the release of poisonous cyanide gas. Now, although it was only meant as a thought experiment, Schrödinger helpfully notes this device must be secured against direct interference by the cat. Anyway, the whole point of the experiment is to magnify the state of the atom up to the state of something macroscopic and tangible. He could have picked anything. It didn't have to be alive, but Schrödinger selected a cat. If the atom decays, the detector detects radiation, releases the poison, and the cat dies. If the atom doesn't decay, the detector doesn't detect radiation, poison is not released, and the cat remains alive. Since the state of the cat and detector apparatus are directly tied to the state of the atom, we say they are entangled. Where things get weird is that according to quantum mechanics, the state of the atom does not have to be either decayed or not decayed. Generally, it's in a superposition of both, decayed and not decayed at the same time, assuming no measurements have been made. This superposition state of the atom gets entangled with the detector, and then the cat. So after some time, the wave function of everything inside the box is in a superposition of the atom has not decayed, poison not released, cat alive state, and the atom has decayed, poison released, cat dead state. So, according to quantum mechanics, the cat really is both alive and dead at the same time. Only when we open the box and make a measurement does the wave function collapse, and the cat actually becomes either dead or alive. These days, Schrödinger's cat is often used as a way to show how weird quantum mechanics is. But that wasn't Schrödinger's point. He wanted to show that quantum mechanics, as formulated, was wrong. So, taking up Schrödinger's argument in this video, I want to show that there is a better way to think about Schrödinger's cat. In fact, a better way to think about quantum mechanics entirely, that I'd argue is more logical and consistent. To get there, we have to examine the three essential components of Schrödinger's cat: superposition, entanglement, and measurement, to see if any of them is flawed. Superposition is the idea that quantum objects can be in two different states at the same time. This seems like a crazy idea and something we'd never observe, but we do indirectly with the double slit experiment. Fire individual electrons through two slits at a screen, and the pattern you see is not just the sum of electrons going separately through one slit and the other slit. It is an interference pattern. The next concept is entanglement. Consider two electrons fired toward each other with equal and opposite velocities. We know they will scatter off each other, but we don't know exactly how. Their trajectories are given by spread-out wave functions that only give us probabilities. But as soon as we measure the momentum of one of the electrons, we immediately know the momentum of the other one. It must be equal and opposite, otherwise conservation of momentum would be violated. Now, this may seem obvious, but consider that before the measurement, the momentum of each electron was in a superposition of states. Measuring one instantaneously collapsed the wave function of the other. And this would be true even if those electrons were light years apart. these electrons are entangled. What's really going on here is that after interacting, the electrons do not have separate wave functions at all. They are described by a single wave function, and this is what it means to be entangled. This explains why measuring one immediately affects the state of the other one, because the single wave function has collapsed. In fact, if we were being rigorous, we'd have to say that there is only one wave function, the wave function of the entire universe, which includes absolutely everything. These are fundamental parts of quantum theory, describing systems with wave functions that evolve according to the Schrödinger equation, which leaves only measurement. Remember, the measurement postulate was added as a second set of rules to connect the mathematics of quantum mechanics to what we actually observe. But doesn't it seem weird that there should be one rule for how systems evolve when we're not looking, and a different rule for when we are? When you boil it down, measurement is just the interaction of one quantum system, electrons and photons, with another quantum system. And we know exactly how to deal with that. We simply evolve their wave functions according to the Schrödinger equation. So what if we throw out all the rules associated with measurement? Well then, in the Schrödinger's cat thought experiment, the radioactive atom in a superposition of decayed and not decayed gets entangled with the detector and in turn the cat. Now remember, we are also made of electrons and atoms which obey the laws of quantum mechanics, so we are quantum mechanical too. So when we open the box, there is no measurement, no wave function collapse. We simply get entangled with the state of everything inside the box. So we see the cat alive, and we see the cat dead. Now, how is that possible? I'm guessing you've never seen both an alive and dead cat before. But the solution is, it's because the you that saw the cat alive and the you that saw it dead actually inhabit separate worlds. By that I mean, they exist in their own complete realities, and those realities will never interact. But where did these separate worlds come from? Well, something I haven't mentioned yet are all the particles of the environment, the air molecules, photons, everything that we are not keeping track of. If a quantum object in a superposition gets entangled with the environment, it is said to undergo environmental decoherence. This branches the wave function of the universe, essentially splitting the universe into two slightly different copies. So, a more realistic account of Schrödinger's cat goes like this. The radioactive atom evolves from 100% not decayed into a quantum superposition of decayed and not decayed. The detector becomes entangled with this superposition state of the atom. But the detector is being bombarded by all these air molecules and photons in the box, which would bounce off differently if it is detected radiation than if it hasn't. So almost immediately, the detector becomes entangled with the state of the environment. It decoheres, branching the wave function in two. At that moment, you are split into two identical copies, one entangled with each outcome of the experiment. You continue to be identical until you open the box, but in this case, the cat actually is alive or dead. You were just finding out by opening the box. What we are unaware of is that the other outcome also happened, just to someone who is not you anymore. I mean, both observers came from you, but they are no longer you, and they're no longer identical to each other. This interpretation of quantum mechanics is called many worlds, and it was formulated by Hugh Everett. And if it's true, the branching of the wave function is happening all the time, so frequently, in fact, that the rate may well be infinite.